Hey there guys, so in the last video we were looking at how to find the coordinates of stationary points on a curve where the gradient is equal to 0. In this video we're going to look at using second order differentiation to determine what type of stationary point they are, a maximum or a minimum, sometimes points of inflection. So in this video I'm really going to take you over the why things are how they are, and in the next video we'll do some real exam type questions on this, but I think it's quite nice to know why things are how they are, because again we've got to a piece of maths that I think is a bit counterintuitive. So, as far as minimums and maximums go, if d squared y by dx squared is greater than 0 at a stationary point, then that point is a minimum. And if d squared y by dx squared is less than 0 at a stationary point, then that point is a maximum. If at a point you get the second derivative equal to 0, then you got a bit of a problem. It's indeterminate what that point is, so we have to get a little bit clever and use another method. So I'm going to have a go here at explaining to you why minimums and maximums work the way that they work, first of all. Okay, so we're going to use really simple examples to illustrate this. Here we've got y equals x squared. Before we get cracking, we need to remember that gradient is a posh maths word for rate of change. So when we're finding the gradient of a curve, we are finding the rate of change of the curve at that point. So when we differentiate again and we get our second derivative, we are finding the rate of change of the gradient. So if the rate of change of the gradient is positive, that means the gradient is increasing as we go from left to right. Or if the rate of change of the gradient is negative, that means the gradient is decreasing from left to right. So we've got a really simple example here. We've got y equals x squared. Now we can see here on the left of the stationary point at 0, 0, the graph is going down from left to right. So we can easily see our gradient is negative over here. So we can say dy by dx is less than 0 to the left of our stationary point. Now, on the stationary point, we know dy by dx is equal to 0. That's the definition of a stationary point. On the lower right, well, the graph is picking back up again. It's now increasing from left to right. So, over here, dy by dx, the gradient of our curve is greater than 0. What's happening here then in terms of the function coming in from the left, it's decreasing until it gets to the stationary point, which hopefully everyone is happy is a minimum. So from the left, it's decreased until it's got down to this minimum point, and then it starts increasing again. So this is what minimums look like. In terms of the gradient, so what's happening with the gradient from left to right? Well, the gradient on the far left started off negative until we got to the stationary point, and then it became positive, and it's getting steeper and steeper the further to the right that we go. So what we can say about the gradient then is from left to right, we can say dy by dx is increasing from left to right. So we would say it has a positive rate of change. Now remember what that's saying. A positive rate of change means that the gradient is positive, but we're already talking about the gradient. So if you like, the gradient of the gradient is positive, or the second derivative will be positive. So this means then d squared y by dx squared at the stationary point must be positive. So let's check. So our graph is y equals x squared. So dy by dx is 2x, and our second derivative, d squared y by dx squared, then is just going to be equal to 2. So that tells us the second derivative is positive anywhere on the graph y equals x squared. So what that tells us is the gradient is always increasing wherever you are on the graph. Most importantly though, it tells us at the stationary point the second derivative is positive, so the stationary point is a minimum. Okay, we're going to use a slightly more exciting example here to show what happens at a maximum. So here we have the graph of y equals minus x squared plus 2x minus 1. Now this chap has a stationary point at 1, 0. Hopefully again we can all see it's a maximum. So what's going on here in terms of the gradient? So to the left of the stationary point, the graph is increasing. So over here, dy by dx is greater than 0. On the stationary point, remember dy by dx is equal to 0, and then on the right of the stationary point, the gradient is negative because the graph is decreasing. So over here, dy by dx is less than 0. It's negative. So what's happening here then? The gradient is changing from positive to 0 to negative. So what's going on here then? Left to right, dy by dx is decreasing. From left to right. So if something is decreasing, it has a negative rate of change. So it has a negative rate of change. Now remember, that is a negative rate of change of the gradient. Therefore, we will find that our second order derivative at the stationary point will be negative. Which is what happens at maximums. So let's check it. So the equation of our curve is minus x squared plus 2x plus 1. So dy by dx will be minus 2x plus 2. And then our second order derivative, so d squared y by dx squared, well, that's just going to be minus 2. So we have a negative rate of change of our gradient as we expected. So hopefully that's helped to explain why these two are the way they are. So again, if our second order derivative is greater than 0 at a stationary point, then that point is a minimum. If our second order derivative is less than 0 at a stationary point, then that point is a maximum. Now we're going to take a quick look at what happens if the second order derivative at a stationary point is equal to 0 and how to tackle it. Okay then, so here we're going to be dealing with y equals x cubed. So what we want to do is find the coordinates of the stationary point and classify it. So first of all, differentiate. So dy by dx is 3x squared. So at a stationary point, dy by dx, so the gradient of the function is equal to 0. So we set 3x squared equal to 0, which quite simply tells us the x coordinate is 0. So the x coordinate of the stationary point is 0. So we would then substitute that into the function to get our y coordinate of the stationary point. Y is 0 cubed, so y is also 0. So the stationary point is at 0, 0, as we all probably knew, and we all probably know what type of stationary point it is. So now, to try and classify it, we want to find the second order derivative. So if dy by dx is 3x squared, and then d squared y by dx squared, oh, that's going to be 6x. So we now find the value of the stationary point by substituting the x coordinate into the second derivative. So d squared y by dx squared when x is 0 is also going to be 0. So that tells us d squared y by dx squared is equal to 0. So it's not positive or negative. So we have a little bit of a problem here. What we're going to do here, we're going to use something called a gradient table to determine what the gradient is doing either side of the stationary point. So remember that dy by dx is 3x squared. And what we're going to do in our table is we're going to have some x values. So we already know when x is 0, we know that dy by dx is 0, because that's our stationary point. So, in terms of the gradient of the line there, it's a horizontal line. So what we're going to do now, we're going to go somewhere to the left of the stationary point. The first nice point there would be -1. So what we're going to do is substitute -1 into 3x squared. So -1 squared is positive 1, multiplied by 3 is going to give us 3. Now that is a positive gradient. So the curve at that point is doing something like that. It's going up from left to right. Now we need to determine what the graph is doing to the right of the stationary point. So let's go to 1. So that's also going to give us 3. So the graph here is also increasing. The gradient is positive. So what this tells us then, the stationary point is a point of inflection because the gradient has the same sort of rate of change either side of the stationary point. So it's positive to the left and positive to the right. So the stationary point is a point of inflection. So you could use gradient tables for maximums and minimums too, but it's a lot quicker just to differentiate twice. So we could even sketch our graph which is y equals x cubed, so something like that. So hopefully this is showing you what we do when the second derivative is 0 at a stationary point, and hopefully this video has helped to explain why the second derivative is positive at a minimum but negative at a maximum. So in the next video we're going to look at classifying stationary points in much more difficult and exam type question curves and functions. Take care guys.